Welcome to the O-Level Chemistry lecture series. Today's topic is on chemical bonding. So before you look through this chemical bonding video and this set of lessons, please make sure that you understand atomic structure well, because much of the concept in atomic structure will be applied in chemical bonding. So for those of you who have read through atomic structure before you started on chemical bonding, we will do a quick recap of some of the terms first before we go into the actual stuff in this topic. So first of all, we must know that atoms always try to lose or gain valence electrons. Take note, they only lose the outermost electrons. This is the outermost electrons to attain the stable noble gas configuration. And this noble gas configuration can be a duplet configuration or can be an octet configuration. Duplet means 2 in the outermost shell, octet means 8 in the outermost shell. For example, this is helium, 2 in the outermost shell. So when they share electrons, earlier it was loss or gain. When they share electrons, when they share valence electrons, again it is to attain the stable noble gas electronic configuration. So you realize that at least for O-level chemistry, most of the chemical bonding or most of the chemical reactions which take place result in the products having a stable noble gas configuration. For example, chlorine by itself has 7 valence electrons. That's why it is in group 7. So when it forms a bond with another chlorine atom, now when we count, it's 1, 2, 3, 4, 5, 6, 7, 8. So this is the stable noble gas configuration. So as I mentioned earlier, it undergoes bonding to attain the stable electronic configuration of a noble gas. And take note, only the valence shell electrons are involved in bonding. The outermost shell involved in bonding. The inner shell electrons are not involved in bonding. So the duplet configuration, 2 outermost electrons. Octet configuration, 8 outermost electrons. So as a result, the compounds which naturally have such a configuration, a duplet or an octet configuration, because there's no need for them to form this configuration anymore, it means that by nature they will be unreactive and very stable. So since there's no need to form a bond with anything else, they exist by themselves as a single atom, and we call it monatomic. Take note, it is monatomic, it is not monoatomic. Okay, there's no O here. So these are the noble gases. Alright, let's move on to the first part of chemical bonding, which is the part on metals. I will cover up to ionic compounds in this first part video. Second part will continue from covalent compounds. So this is an example of metal. You should know this is gold. Gold is a metal. So what gives the metal its structure is basically the metallic bonding. The metallic bonding within the structure itself. So how is a metallic bond formed? How is a metallic bond formed? Basically all bonds, regardless of metallic, ionic, covalent, they are basically attractive forces between the nucleus, or between some positively charged element and some negatively charged element. So in this case, the negatively charged element would be the negatively charged electrons. And for metals, it is rather specific. It is the positively charged metal ions attracting the negatively charged delocalized mobile valence electrons. It seems like a mouthful, but if you look at the diagram here, you will see that it is quite obvious. So this is the structure of a metal. These are the metal cations. When they are in the structure, of the metal, they lose some of the valence electrons into this, what we call the sea of valence electrons. So electrons are negatively charged. The metal cations are positively charged. So it means that there exists a electrostatic attraction between the positive and the negative charges. So this sum of all the different attractive forces here gives rise to the metallic bonds. So as I mentioned earlier, metals tend to lose electrons. So they lose electrons when in the structure, so we call them electropositive. It means that they tend to form positive cations or positive ions. Positive ions are cations. Over here, and this is the attractive force between the cations and the electron in the C or D localized mobile valence electrons. And because the positive charge cation can attract the surrounding region of electrons, and this electron here attracts the surrounding regions of cations, it means that the metallic bond is actually non-directional. So if I were to have a magnet, north pole, magnet, south pole, the magnet attracts this way, right? Or the other way, up to you. If I were to shift the magnet over to one side, to the other side, over here, if I keep this pole here and shift it over here, it will not attract anymore. So this is a one way, this is something similar to a directional attraction. So if you imagine that this is a single bond, this bond cannot form anywhere else around the magnet. But for cations and cations and electrons, the attractive force is actually all around. So it's non-directional. This is quite important later on when we go into the properties of the metals. So keep this in mind. Alright, so now let's touch on some of the physical structures of metals. Actually, the physical appearances, the physical structure, the physical properties comes about because of the bonding in the metal structure. Right? So metals are lustrous, they are shiny and sonorous. Sonorous means that when you hit them, they produce a sound. For example, cymbals. You wouldn't make cymbals from wood or from plastic. You wouldn't have the clanging sound when you make them from brass. So metals are lustrous. Lustrous means it's shiny. Why is it lustrous? This one is more about A-level concept. It's basically because of the number of electrons that metals have, and the electrons are located in orbitals of much higher energy levels. If you want to find out more, you can read up more about this in the A-level notes that you can find quite readily in popular or maybe online. Metals have a high density. It is quite obvious when we draw the structure out. You notice the cations are all arranged pretty orderly, and the electrons are located all around. So this close packing of the cations in the metal lattice structure gives rise to a high density. As you know, density equals to mass per unit volume. So in the same unit volume, I have lots of cations packed inside. So I have a high mass, same volume, density will be much higher compared to something else with the same volume but lower mass. They're malleable and ductile. This one is important. This one actually comes about because of the non-directional nature of the metallic bond. So as I mentioned earlier, the electron can attract the cation can attract the electron, and it can attract all around, anywhere. It doesn't need to be in one single line. It can be anywhere, which means that if I were to push one layer, until the layer slides, this electron here can still attract this cation. This cation here can still attract this electron. So all in all, the non-directional nature of the metallic bond prevents the layers from breaking apart. Okay, so the layers can slide without breaking apart. This gives rise to its malleable and ductile properties. Malleable basically means that if you hit the metal, it dents without breaking. If you compare this to glass, if you hit the glass hard enough, the glass will shatter and break. So glass is not malleable. Ductile means having the ability to be put into a long wire. Copper wires. So why are metals used to make wires? Because they are ductile. One of the properties is ductility. They are ductile, and of course, they must be able to conduct electricity. So metals have high melting and boiling points. This is quite obvious. The electrostatic forces of attraction between the cations and anions is really high. So you need a lot of energy to overcome these forces. As a result, it has a high melting and boiling point. Obviously, metals are not soluble in water and organic solvents, and they have good electrical conductivity. So earlier, when I drew the structure out for the metals, if you were alert and you were fast enough, you will realize that because the electrons here are what we call delocalized, it means that they are not stuck onto one spot. They can move about the metal structure. It means that if I were to put a positive charge, a positive terminal here and a negative terminal here, the electrons will migrate in this direction, right? So this migration of electrons actually constitutes the electric current. So metals can conduct electricity because they have mobile valence electrons which can migrate freely through the metal lattice structure when I apply a potential difference across the metal. And if we take a closer look, you will see that as the metals lose more valence electrons per atom, the conductivity actually goes up. So aluminium forms Al3+, magnesium forms Mg2+, sodium forms Na+. The number of valence electrons they can contribute into the sea of delocalized electrons increases. As a result, the conductivity also increases. Another property of metals, because of the mobile valence electrons, is the good thermal conductivity nature. So you should know that metals are used to make pots and pans, cookingware. Why? Because they can conduct heat really well. So if you compare this structure here, maybe to a structure of a block of wood, probably would have the particles closely packed. So metals are also closely packed particles. But why does metals conduct much better than a block of wood? It's because we have these valence electrons which can migrate. So imagine if I were to apply a heat source here, this electron here will vibrate really fast. It will gain kinetic energy. It will move faster. And it can collide with the surrounding electrons, or you can even move through the structure. So when this happens, the heat energy is transferred across the metal block. And because we have this large number of mobile valence electrons, this transfer of heat is actually very fast. Because if it moves and it hits this one, it moves, hits this one, moves, hits this one, moves, hits this one, moves, hits this one, and so on and so forth, it's really fast. Or this electron can actually migrate through the structure. So the sum of all these parts together allows the metal to conduct heat much better than a non-metal. Okay. Alright, the next thing I need to mention is about alloys. So earlier I showed you this is something that is a little bit off topic for now, but it will come in useful later on. So alloys are basically mixtures of metals and non-metals. This is a lock you see here. The golden color part is actually brass. Brass is a mixture of copper and zinc. So when these two metals are mixed together, it becomes harder than each individual metal alone. Why is that so? Because, first of all, the particles of the different metals are of different sizes. So imagine if I have a lattice that is this ordered and this nice. If I exert a force, the layer can easily slide. But what happens if I have one obstruction within the lattice structure? So when I exert a force, this layer can't really slide because it is obstructed by this different size particle. So alloying basically does the same thing. The different size particle prevents the layers from sliding. Why? Because it disrupts the orderly arrangement of the layers. So as a result, the layers can't slide. If it can't slide, it means it is less malleable, it's less ductile, it is harder than the original metal. Some examples of alloys here. Okay, let's move on to ionic bonding. This one is a pretty important area for this topic, together with covalent bonding. Ionic bond, as the term implies, ionic. It means that it involves ions. It is a bonding which involves ions. So ions, you have learned before, there's positive and there's negative. So this is the cation ion, this is the anion. So plus and minus, they will attract. So basically the ionic bonding is the electrostatic attraction between the positively charged ion, which is the cation, and the negatively charged ion, which is the anion. So this attractive force between these two ions constitutes the ionic bond. And again, electrostatic attractions are strong. Straight away you will realize that this means that it must have a high melting and boiling point. Okay, infer from the definition the properties of the substance. The next thing you will need to know is how the ionic bond is formed. Okay, it is formed when electrons are transferred from one atom to another atom. And this is usually metal and non-metal. So electrons are transferred from the metal to the non-metal. For example, sodium chloride. This is an ionic compound. Sodium has 1 valence electron. Chlorine has 7 valence electron. Chlorine has 7 valence electrons. So during the ionic bond formation, this electron from sodium is lost to chlorine, and sodium forms Na plus, chlorine forms Cl minus. And this plus and minus, they attract, giving rise to the ionic bond. So why is it plus? Because originally, number of electrons and number of protons was balanced. So the charges cancelled out. But when you lose one electron, which is negative charge, you have one proton in the nucleus of sodium which is not balanced, as a result, positive charge. Chlorine, 7 valence electrons, together with the other electrons, balances out the number of protons it has. But now I add in one extra electron from sodium, gives it an extra negative charge. That's why it's Cl minus. Okay? And the diagram you show here will be important later on. You notice that the plus attracts the minus, minus attracts the plus, and this is quite an orderly arrangement. So imagine what happens if I were to shift the layer one side. Imagine what happens. Think about this first. We will touch on this later on. What happens when the layer slides? Just one single ion to the right. What happens? Or what could happen? So as I mentioned earlier, ionic bonds usually form between metallic and non-metallic elements. Why? Because metals, remember, it is electropositive. They tend to lose electrons. So in nature, if something loses electrons, something else will want to gain the electrons. So these are the non-metals. So non-metals are what we call electronegative. They like to gain electrons, and this actually makes them a perfect couple. Metals lose electrons, non-metals gain electrons. They form cations, they form anions, and they come to be attracted together by this strong electrostatic interaction, which we call the ionic bond. Okay, so take a look at your periodic table. You will find the metals in groups 1, 2, 3, and non-metals in groups 7, 6, and 7. Some examples here: sodium loses 1 electron, Mg loses 2 electrons, Al loses 3 electrons. If chlorine gains 1 electron to form Cl minus, it can form an ionic compound with any of the elements, any of the ions above. Same for the O2 minus or the oxide ion. This is the chloride ion. Okay. And obviously, the positive and negative charges must be equal in an ionic compound. So if Na plus, Cl minus, it will be NaCl. So one is plus, one is minus. Overall, it's 0. Mg, Cl. Mg is 2 plus, Cl is minus. Overall is 1 positive. Not correct. How do we get rid of this extra positive charge? We need one more chlorine. So MgCl2, 2 plus, 2 minus. Overall is 0. So this is good. Okay, so an ionic compound must be neutral. The compound itself must be charge neutral. It must be charge neutral. If it has a charge, it is called an ion. Okay, the next thing you see here is actually dot and cross diagram. Sometimes you will be asked to represent the ionic bonds or even the ionic bond formation, even covalent bond formation with dot and cross diagrams. How do we draw them? It's actually quite simple and very straightforward. So if you take a look at an example of NaCl, formation of NaCl, Na has 3 electron shells, 1, 2, 3, of which the outermost shell has 1 valence electron. Okay, chlorine has, again, 1, 2, 3, 3 electron shells, of which outermost has 7 valence electrons. So remember, first rule, when the elements react, they try to form the stable noble gas configuration, either an octet or a duplet. So if sodium were to lose 1 electron, how many would be in the next shell? If it loses this electron, how many will be in the next shell? It will be 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Duplet, octet configuration. So this electron that's lost is transferred over to chlorine. So when chlorine gains this electron, how many does it have in its valence shell now? 1, 2, 3, 4, 5, 6, and 7, 8. Octet. Perfect. So Na plus and Cl minus are the stable ion forms, and they come together to give you your sodium chloride. So why doesn't sodium try to gain 7 more electrons? If it loses 1 electron, it can form the stable octet configuration. If it gains 1, 2, 3, 4, 5, 6, 7, if it gains 7 more electrons, it can also form the stable noble gas configuration. But if you imagine this, is it easier for you to lose one thing than to get 7 items? Yes, it is, right? Correct? So it's easier for you to spend 10 cents than to earn 70 cents. Similar concept in nature, it's easier for sodium to lose just the 1 outermost electron than to gain 7 electrons. So this applies for chlorine. It is easier for chlorine to gain 1 electron than to lose 7. It is energetically more favorable. This is the term you will use in A levels. It is energetically more favorable for chlorine to gain 1 electron than to lose 7 electrons. So as a result, it forms Cl minus Na plus, and we have the NaCl ionic compound. Of course, an ionic compound doesn't have just NaCl, one of each alone. Okay, the structure is huge and massive. In one single grain of salt, there will probably be a few billion or few trillion Na plus and Cl minus ions. So all this come together to give you your ionic compound. So how do we draw? Very simple. We show the valence shell electrons only. 1 electron is transferred to chlorine. As a result, it forms Na plus and Cl minus. The sodium's next inner shell has 8 electrons. We show the 8 electrons here. And we slap the positive charge on the ion because it has lost 1 electron. We slap the negative charge on the chlorine atom now to give the chloride ion because it has gained 1 electron from sodium. Okay. Last but not least, make sure you have the key, no marks, because nobody knows what your dot means, nobody knows what your cross means. Please write the correct key as well, and use different electron drawings to differentiate the different elements. Dot, cross, dot, triangle, dot, square, up to you, so long as you distinguish the 2 different elements here. Okay, so now please try checkpoint 1. You can pause the video now to attempt the checkpoint. Continue with the video when you are done. So for checkpoint 1, you're supposed to draw the dot and cross diagram for lithium bromide, LiBr, calcium oxide, and MgF2. Okay, this is lithium bromide. This is calcium oxide. And this is magnesium fluoride. Are the names important? Yes, they are. So as we go along the way, please try to make a mental note of how I name the compounds. Lithium is because it's lithium Li, Br is bromine, but in the ion form, I always call it a IDE. So bromide, chloride, iodide. Calcium, this is oxygen. In the ion form, again IDE, so oxide. Magnesium fluoride. Right, so let's draw the first one, lithium bromide. Lithium is in group 1. Lithium is in group 1, which means that it has one valence electron. It has one valence electron. Bromine is in group 7. It has 7 valence electrons. So from this we know that this is a metal. Metals have usually 1 to 3 valence electrons. Non-metals have 5 to 8 valence electrons. So if we see this is a metal, this is a non-metal. Metal, non-metal, ionic bonding. Ionic bonding involves the transfer of electrons from the metal to the non-metal. So this electron is transferred to bromine, and we have lithium bromide. Lithium is positively charged, bromide is negatively charged, LIBR. If you want to show the valence electrons of lithium here, no problem, please go ahead. It is also okay. Calcium oxide is the next one. Calcium is in group 2. It's in group 2. So it has 2 valence electrons. Oxygen is in group 6. There are 6 valence electrons. So metal, non-metal, ionic bonding. Ionic bonding, lose electrons to oxygen to give you your stable noble gas configuration. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons. It needs 2 more. Just nice. Calcium can give oxygen 2 more electrons. So it will look like this. This is the next innermost shell of calcium. 2 plus because it has lost 2 electrons. Oxygen 2 minus because it has gained 2 valence electrons from calcium. So overall Ca2 plus, O2 minus, CaO, charge balance, good. The other one, magnesium fluoride, MgF2. Mg is in group 2, so again 2 valence electrons. Fluorine is in group 7, 7 valence electrons. Can fluorine take both electrons from magnesium? No. Why? 7 plus 1 plus 1 equals to 9. What is the stable configuration? It is 8, which means each fluorine atom can only gain 1 valence electrons. But magnesium has 2 to give away. So what happens? Very easy. Basically, 2 fluorine atoms come and react with your magnesium. So 1 electron goes to this one, and 1 electron goes to this one, which means overall at the end of the day you have Mg 2 plus again, and F minus, 2 of them. So overall charge balance MgCl2, 2 plus minus times 2. Overall we get 0. Right? Simple and straightforward. With the properties, with the chemical, with the bonding, with the ionic bond, with the description of the ionic bond, with the way the ionic bond is actually formed, we can also deduce the structure of the ionic compounds. So first of all, let's look at the structure of the ionic compound first, of any ionic compound. It will be positive cations with a anion beside, plus minus, plus minus, plus minus, plus minus, so on and so forth. So if I simplify this diagram, let's say I just draw this 4, this 2, and the 2 that are below this, it will look something like this. Minus, plus, minus, plus, plus here, minus here, plus here, and minus here. So notice that the cations can attract the neighboring anions. So all this attraction gives rise to the ionic bond, and they are arranged in an orderly manner. Why? Because if it is not orderly, the bonds will break. Because the attractive nature of ionic bonds are directional. They are directional. It is unlike metals, which is non-directional. This is directional bonding. If I shift it a little bit, the layer will split apart. Okay, think about this. Think about this. One layer, one layer, one layer. What happens when I shift just one single layer to the right by 1 unit? Three-dimensional structure, giant crystal lattice. Okay, so earlier was the structure of ionic compounds. The structure and the way ionic bonds are formed gives rise to the physical properties. Hard and brittle. Why hard? Because strong electrostatic forces of attraction require a lot of energy to be broken, so it's hard. Why brittle? Why brittle? Later on we'll take a look into this one. High melting and high boiling points. Same thing, because it has strong electrostatic forces of attraction. You need a lot of energy to break these attractive forces. As a result, your MP and BP are high. Conducts electricity in molten and aqueous states, but not in solid state. Why? Think about this. How does a metal conduct electricity? It is through the migration of mobile valence electrons. Are there any mobile valence electrons in ionic compounds? If there are no mobile valence electrons in ionic compounds, how then does an ionic compound conduct electricity? Okay, think about this and relate this to the structure of the metal. For example, sodium, iron, copper. Next thing, ionic compounds are generally soluble in water. For example, NaCl, of course it must be soluble in water. You put this into your food. Soluble in polar solvents. What are polar solvents? For O levels, not yet. It is not yet. You need to know what. You don't really need to know what are polar solvents. But for now, water. Take note, water is a polar solvent. Water is a polar solvent, and it is insoluble in non-polar solvents. Non-polar solvents are basically solvents made of organic compounds. You can take a look at the organic chemistry videos and you will see some examples of non-polar solvents. One simple example would be hexane and alkane. Right, the first one, hard. Why is it hard? As I mentioned earlier, strong electrostatic attraction. You need a lot of energy to break these attractive forces. Why is it brittle? So if it's plus minus, plus minus, plus minus, minus plus, minus plus, minus plus, and it slides to become plus minus, plus minus, plus minus, minus plus, minus plus, minus plus, minus plus. What actually happens? The layers have, in fact, aligned themselves such that the plus is with the plus, minus with the minus. There can no longer be an attractive interaction. Plus and plus will repel, so we get an immediate shattering of an ionic compound. That's why we say that ionic compounds are brittle. Okay, they are brittle. Why? Layers of ions slide. They bring ions and light charges next to each other. As a result, the charges repel. Okay, charges repel, layers split apart, and it shatters. So let's take a look. Push, repel, 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 breaks apart, shattering. So this property comes along with its strength of the electrostatic forces of attraction, high melting and boiling point, a lot of energy. That's why if you look at this here, this is a diagram of this is a picture of a furnace. In the furnace, it is lined with many bricks here. These bricks are called refractory bricks. Refractory material basically means that it can withstand a very high temperature. So why can it withstand a very high temperature? It is an ionic compound, strong electrostatic force of attraction between the cations and anions, which requires a large amount of energy to be overcome. Hence, it has a high melting and boiling point. That's why we can use it in the furnace to line the inside of the furnace. The furnace can get pretty hot when it is working. The next property of ionic compounds is that it conducts electricity in molten and aqueous states only, but not in solid state. Why? If you recall the earlier diagram, the ionic lattice is actually a 3D structure. They are held in a fixed position. So, For metals, it conducts electricity because electrons can migrate. But if you recall, ions, plus and minus, they are also charges. So if the ions can migrate, they can also carry a charge. But they cannot migrate if they are stuck in their positions in the 3D crystal lattice structure. Okay, so in solid state, the ions are held in fixed positions. They cannot move. They are held in fixed positions in the giant ionic crystal lattice by what? By strong electrostatic forces of attraction. As a result, what happens? It means that it cannot move. It means that it cannot conduct electricity. Okay, so in order for an ionic compound to conduct electricity, first thing you must do is you must break the ionic bonds. You must break this very strong electrostatic forces of attraction. Once they are broken, it scatters into ions. If I were to put a plus here and I put a minus here, the plus will migrate to the minus will migrate to the plus. This migration of charges actually constitutes the flow of electric current. So molten NaCl, molten means liquid state, it is no longer a block of solid. So how does it melt? It means that it must have additional. How does it melt? It melts because the bonds are broken. They are no longer there's heat given in, it melts. Bonds broken, it melts. They split apart. They are no longer held in fixed positions. So when you apply a charge across, they can migrate and they can conduct electricity. Aqueous states is the same. When I dissolve a block of sodium chloride in water, the block disappears. Why does it disappear? Because the individual ions are out of the block. So when it is individual ions, again, when I apply plus, apply minus, they will migrate, carry a charge. This is the electric current flow. Okay, this is the electric current flow. So ionic compounds conducts in both molten and aqueous states. Just a quick one over here. Generally soluble in water and polar solvents. NaCl, for example, soluble in water. Insoluble in organic solvents. Okay, for example, hexane. This is an organic compound. This is also a hydrocarbon. A hydrocarbon is made up of only hydrogens and carbon. So hexane is a hydrocarbon. What is the structure of hexane? Watch the Organic Chem series videos to find out more. This is in the topic of alkanes. So this reason is why ionic compounds dissolve in water. It is not in the O-level syllabus. It is basically because of the formation of ion-dipole interactions. If you want to find out more, check out the dipole nature of water molecules. Okay, the dipole nature of water molecules. And with this, you can find out why ionic compounds tend to dissolve in polar solvents. Alright, we have come to covalent bonding. This will be the next part of the lecture series. I will stop here for now.